this is complex analysis. We are going to move to the next topic, the so-called integration along a path or path integrals. Classically, they are also called contour integration, contour integral, etc. But I think modern terminology is a path integral. So we will look at some examples. Before I go further, there had been some queries about integration along a path, saying that when we talk about integration of a non-negative function in Riemann integral of a real valued function, of course non-negative, yeah, there is a geometric interpretation. That's a okay, it's a area of a region enclosed by the graph, okay, x-axis and x equal to a, x equal to b, etc. Right, but is there any kind of geometric interpretation? Okay, there is no geometric interpretation, but there are physical interpretations. Okay, if you learn vector calculus, okay, line integral, etc., then you might have learned something like two words which you might have learned: work done by a force and also flux of a fluid motion, etc. These things can be explained. Okay, but in my practice, what I believe is that don't be hung up on such things. You try to understand what the definition is, try to learn how to work with it rather than resist understand. Okay, I should have some meaning, etc. Okay, you will see its power as we go along. Sometime I will try to explain on the way when we deal with Cauchy's theorem via Green's theorem. I will try to explain a bit of that, but my sincere suggestion, advice would be, okay, accept it. This is, again, I will give a real life analogy. I have seen in many Indians when they go abroad, let's say 2 years, USA, then whatever they buy, they try to immediately convert in terms of Indian rupees. Okay, then they say, oh my gosh, it's 300 rupees, 400 rupees, etc. Right? But that's not the way. So slowly they will get used to thinking in terms of dollars. Okay, this is only $2 or $4, like that. Okay, that's a way to look at it rather than converting to what you already know and trying to compare and contrast. You think about these things. Okay, you should be ready to adapt yourself rather than resisting it. Okay, with this preliminaries, let me get started. So many of you might have seen my analysis, topology lectures. Okay, then by a path, what we mean is it's a continuous function from an interval to some topological space. Here we are going to talk about it, u. This is continuous. Okay, any such map is called a path. Notice that path is a continuous map from an interval to some topological space. In particular, we are going to deal with open sets in C. So we say gamma is a path in U. Okay, but this is for complex analysis. This is not the kind of path we are going to look at. Okay, what we are going to look at is, we are going to look at, suppose on AB you have a finite partition, okay, T0, T1, Tn equal to B, so that when I restrict gamma to Ti minus 1 to Ti, I less than or equal to, no, I 1 less than or equal to I less than or equal to n, I believe. Yeah, right. Then this is continuously differentiable. What does it mean? Gamma prime T exists and T going to gamma prime T is continuous, where on each of the Ti minus 1 to Ti. Alright. So again, you should know, understand pictorially what does that mean is the following. So at T1, when I, let's say for example T1, this is my T1, this is my T0, or okay, Ti minus 1, Ti and Ti plus 1, right? When I go from here, the curve may look like this, and when I go from here, the curve may, that is the tangent gamma prime Ti, when I come from this side, may be different from gamma prime ti when I come from this side. Of course, you can say left derivative and right derivative, etc. But try to understand. Okay. So when I think of gamma prime ti as ti is a part of this interval, ti minus 1 to ti, and ti is a part of the interval ti to ti plus 1. Okay. This may be different. Okay. So tangents not be. So one calls this a piecewise C1 path or piecewise smooth path. Or C1 path. So hereafter, whenever I say path in complex analysis, we will mean, we shall mean piecewise C1 path. Okay. Therefore, again let us look at gamma. First of all, it should be continuous from a bit to u. This is already assumed. And gamma restricted to ti minus 1 to ti is C1, continuously differentiable. Keep that in mind. Okay, we will give examples. Okay, right. The the first example is, of course, easy one. Gamma from, let's say, a b to u, and fix a point z naught in u. Then define gamma t equal to z naught for all t in 0 1. Then this is called constant path, right? And remember, gamma prime exists everywhere, and gamma prime t is 0 for all t in AB. Therefore, this is a path. Path according to our definition is piecewise smooth, but here it's actually C1 on the entire interval, right? The second example is, okay, line segment. Fix 2 points Z and W in U. Okay, assume the line segment. This we had already defined. This is of form Z plus T times W minus Z, 0 less than equal to T less than equal to 1. Assume this lies in the U. Okay, then this is called the line segment from Z to W, right? Okay, so let us define gamma t to be Z plus T into W minus Z, 0 less than equal to T less than equal to 1. Okay, and again with this we had already seen what is gamma prime t. If you remember, when we talked about functions from an interval to C, we looked at this kind of examples. So this is W minus Z, right? Therefore gamma prime is actually constant, therefore it is gamma is C1 on 0 1. Okay, and one usually think in two variable calculus or n variable calculus, we always think of this as a tangent vector. So when I said piecewise smooth, what it means is at the end points of the partitioning intervals, okay, the tangents may differ if you approach from the left side or if you approach from the right side. That's what. Otherwise, it's well behaved. But remember, we want it to be continuous for the entire interval. That we are not going to violate. Is it okay? Third example. Okay. Fix a natural number, sorry, an integer. Define gamma n to be 0 to 2 pi to C. Okay. So that gamma n of t is e per 2 pi I n times t. Oh, sorry, e per I n t. There is already 2 pi, so it's just e per I n t. Okay, right. So this is again a path, because we know that gamma n prime t we can differentiate as I n times e per I n t. So gamma is C1 on 0 to pi. So these are all paths. Okay. Now is the time we have to explain something very interesting. What we want to say is, when we say, remember, when I say it's a path, okay, it's a map. Okay, even though geometrically I may think of this. So for example, this is my U, and I can't take these two points. If Z and W, this may not be there, but suppose my Z and W are here, then this is a line segment. Okay, this is the line segment here, but that's not to be confused with this, because path is a map. Okay, therefore we have to have thing, and let us do, this is a standard note, my notation it is in my book. This is by definition is gamma t as t varies in the its domain. So this is a subset of u. Okay, this we call as a track or trace of the path. So what I am trying to say is, when I talk about a path, it is a map. That's what you should remember. But even though for geometric reasons we may trace gamma t, okay, as t varies over AB, and find the subset, okay, subset, okay, and we may think of it. For example, in the first case it's a constant z0, whereas in the second case is a line segment. In the third case, you can see this is why it's very important. Let us say gamma n. This you can see this is nothing other than for each n. This is the third example. Gamma n. This is a circle, right? It just z in c so that mod z equal to 1. You see that for each and every n except n equal to n not equal to 0. Yeah, because n equal to 0, it is just e power 0 it, which is just constant 1. Okay, whereas gamma 0 is constant path. Okay, constant path at 1. That means gamma naught of t is 1 for all t. Okay, do you see that? But as paths, gamma n's are different. For every n actually. Okay, to show that, because they are distinct. What does it mean? As functions they are distinct. That means you can always find a t so that gamma n of t, if n and m are different, gamma n of t is different from gamma m of t. That you can do it, right? Very easy. All right. So what is the first thing? Our definition of a path is a continuous map from an interval to an open set. Okay, path in U is a continuous map from an interval in R to U, so that gamma is piecewise smooth on the interval AB. What does that mean? On that interval, I can break it into a partition. On each of the partitioning subinterval, it is C1. Okay, so what is that I have to remember? At the common endpoints, okay, of the subintervals, partitioning subintervals, gamma prime t, which as I approach from the left side or from the right side, left derivative and right derivative may differ. Okay, we will look at an example. That's going to be the next example. And the next point I wanted to say is, we should never confuse a path and track. Okay, they are distinct. Okay, the usual standard example which I give is, a track is like a railway track. Okay, from a city A to another city B, right? But there are many trains. The train, okay, that train 1 may leave at 8 a.m. and reach at 11 a.m. and train 2 may leave at 10 p.m. and reach at 12:30 a.m. Okay, but what is the track? The track is the same, but you cannot say I will take the train. You have to say I will take the track. You have to say which train you are going to take. So paths are like trains and tracks are the railway lines. Okay, many trains may use the same railway line, but the trains are different, right? You cannot get into buy a ticket for local train and get into a Rajdhani. Right, just for fun. Okay, so if you notice, so far we had given all our paths are completely C1. Okay, nothing to do with piecewise C1. And in complex analysis, piecewise C1 paths are going to play an important role. So let us give some two simple examples which will give you the idea. Okay, yeah. So this may be example 4. I hope so. What I want to do is, this is the thing. So I want to go from 0. This is my 1. This is my 1 plus I. Here I want to travel. So what is it I want to do? I want to take gamma from 0 to 2. So 0 to 1. So I'm going to split it into 0 to 2. And 0 to 1 I will travel from here to reach here. And from time 1 to 2 I will travel from 1 to this. So how will I define that? Gamma t. Of course, this is very easy. T is in 0 1, and here what should I do? So I should start from 1. This will remain constant, only the ith variable, that is in the imaginary variable, I have to increase, but then I have to start at time t equal to 1 and time t equal to 2. I should reach there, right? Therefore what should I do? I times t minus 1. Notice that when t equal to 1, then we are at 1, and when t equal to 2, we are at t minus 1 is 2 1, then 1 plus I. Okay, this is for t in 0 to 2. And is this continuous? Is gamma continuous? The only thing is gamma is continuous at t equal to 1, right? Because at t equal to 1, gamma 1 is 1, and in this portion also it's going to be 1, right? Therefore gamma is continuous on 0 to 2, and gamma is piecewise smooth, piecewise C1, because gamma prime t is 1 on 0 1 and equal to I, right? 1 it minus 1, so this is going to be I on 1 2. Now you can see that gamma prime, if you think of it as a complex tangent vector, it is going to be 1 here, as you can expect. Okay, this will be the direction here, whereas when I'm going here it should be in the ith direction. Yeah, we captured it. That's what we meant by the tangents at the common endpoints may differ, but the function is continuous. Yeah. So one more example, that should be enough. We will stop with that. So one more example will be something again which will be similar. So let us say it's a minus 1 and plus 1, and then from 1 I'm going. So I'm going to take the semicircle, and then I'm going from 1 to 2. Okay, right. So how will I do that? So let us do that. So gamma t. Okay. So this is, remember, it's a pi, therefore e power I pi, and this may be t, and t equal to, maybe I should write 1 minus t. When t equal to 0, I pi, therefore I will be minus, and when t equal to half, I will be half, therefore I pi by 2. When t equal to 1, it will be 0, therefore 1 minus t. Okay, 0 less than or equal to t, less than or equal to 1. And after this is just a t for 1 less than or equal to t less than or equal to 2. Again you can check gamma at 0 is 1. Okay, either I come from this side when t equal to 1, and when I put t equal to 1, and gamma prime t, you know how to compute, let's not worry about. E power minus I pi t, therefore I pi minus into e power I pi 1 minus t, etc. Okay, and therefore at t equal to 1, okay, this is just when t equal to 1, what is this? T equal to 1, this is 0, therefore it's I pi. When I am coming from the on the interval 0 1, whereas on the interval 1 2, it is going to be 1. Yes, yeah, yeah. So the interval is going to be minus I pi, because I am going from here. So it's going to be, see, it goes from here to here, therefore the tangent vector indirectly is going in the I direction. But if the speed is pi, it's not the unit speed, right? If you don't understand this words, forget it, you are computed, right? So we have done all these things. So these are the typical examples. So pause, review, and proceed. Okay. So if you want, I will give an exercise. Think of this path. It starts from here, and this is 1 0, that is complex number 1. This is complex number I. So I want you to think of a path which goes from here to here, and here to here, and here to here, right? It's up to you what interval you use, etc. So gamma t, so gamma should be something, okay, maybe 0 to 3, 0 to 1 you may go from here, 1 to 2 you may go from here to here, or 2 and 2 to 3 you may come from here to here, etc. And such that gamma 0 is gamma 3 is again 0. Think of such a path, okay? So we will, next one we want to do is something again, concatenation or juxtaposition of paths. See, for example, I want to travel from one town to another town, okay? I may not have a direct train. What I may do is I may take some train from here to here and then take a connecting train to go here, right? Therefore finally I have a path from here to here, a train from here to here, except it's a, I put paths together. So that's a kind of idea I want to have. Just okay, let us understand what is concatenation meaning. I mean, if you have gone through a programming language move and you have learned with the strings, then concatenation, you concatenate, you might have learned, right? Put one string and immediately follow the second string. Juxtaposition meaning keeping side by side. Okay, they are the same thing. Okay, how will I define? Suppose gamma is defined from A1 to B1 to some interval u. Okay, some not interval, open set. Okay, so A1 to B1. This is my A1, this is my B1, and this is from this point to this point. Gamma A1, this is gamma B1, right? Now gamma 2, I'm just drawing the picture. My A2 may B2 may be like this, A2 B2 may be like this, A2 B2 may be like this. Okay, so just so that I don't want to confuse you, let me say A2 B2. This is my gamma 1, and gamma 2 is also a path, but what it does, okay, maybe I should use the words, this is gamma B1 is called the end point or the terminal point, and gamma A1 is called initial point. So the terminal point of gamma 1 I want it to be the initial point of gamma 2, that is the gamma 2 of A1. So it starts from here. So let me just put a different color. This may be my gamma 2, right? So pictorially I can see I have a path from gamma 1 A1 to gamma 2 B2. This is, so let us do, this is gamma 2 A2, this is gamma 2 B2. So if you call this as a point P and this is Q, then I have a path from P to Q, right? There is an intermediate point which is gamma B1, gamma 1 B1, which is same as gamma 2 A2, right? Okay. Now I want to write a single path. How will I do that? Okay. So that's very easy again. So what we do is, let me take A1 B1, right? As I said, A2 B2 may be I'll draw a picture so that even if it confuses, the A to B2 may be this, or A to B2 may be this, or A to B2 may be this, or A to B2 may be this. You understand that? It may be any way. So what I do is, let's start with A1 B1. Okay, now let's look at A to B2. What is the length of this interval? B2 minus A2. Therefore what do I do is, I create an interval, I put that interval here. That is, from B1 I travel B1 plus B2 minus A2. Then this is exactly the length of this interval is B2 minus A2. Right? Length of this interval is this. Have you understood? So I am going to define a path, new path gamma, which is from A1 and B1 plus B2 minus A2 to U. Yeah. So how will I define? So gamma of t on A up to A1 B1 I don't have to worry about it. It is gamma 1 of t for t in A1 B1. And for gamma 2, what do I do? So I have to define gamma 2 of what should happen. So if I take a t here, right, that the t is greater than b1, therefore I should simply say t minus b1. What do I want? Yeah, so I have to say it should start, gamma 2 should start with a2, right? Therefore gamma 2, so I should start with a2 and then t minus b1. When t equal to, yeah, when t equal to b1, this is gamma 2. So notice that gamma 2, when t equal to b1, this object is gamma 2 a2. When t equal to b1 plus b2 minus a2, right, you see that this is going to be gamma 2 a2 b1 plus b2 minus a2 minus b1, therefore b1 b1 cancels, a2 a2 cancels, gamma 2 b2. Do you follow that? Just make sure you understand. Okay, I am explaining you how I did that instead of simply memorizing such a formula. Okay, so let me rewrite it again. So gamma of t is gamma 1 of t for t in a1 to b1, and here it's gamma 2 of t. You have to make sure it makes sense, right? This is, see, sorry, this is gamma 2 of, I have to start with where? I have to start with a2 plus t minus b1. This is where t is between b1 plus whatever I wrote, b1 plus b2 minus a2. Yes, and so what I am doing, what is gamma t at t equal to b1 is what I am looking at. That is same as gamma 2 at a2 plus b1 minus b1, which is gamma 2 a2, which is gamma 1 b1 by assumption. This is by hypothesis. Okay, this proves continuity. Do all of you understand? Next, and what is this at the end point? b1 plus b2 minus a2. This is going to be gamma 2 of a plus t. T is going to be b1 plus b2 minus a2 minus b1. Right? Therefore a2 cancels, b2 b1 b1 cancel. Therefore I am getting it gamma 2 b2. Yeah. Okay. Therefore what I have shown is gamma is from the interval a1 b1 plus b2 minus a2 to u, so that gamma of a1 is gamma 1 of a1 and gamma of b1 plus b2 minus a2 is gamma 2 of b2. Is that okay? There, and it's continuous. For continuity, I only have to check at the common endpoint, which is b1. We checked it. Okay, right. And it's of course PSO is differentiable. When I restrict gamma to a1 b1, this is nothing other than gamma 1. Therefore, it is c1 because I assume my gamma 1 is differentiable. And I restrict to this the interval b1 to b1 plus b2 minus a2. Do you remember how to write it? Endpoint b1 and then add the length of b2 minus a2. That's the length of the second interval. So that's a mnemonic for you to remember. Okay, this is what is the map? This is t going to go back. T going to b1 plus t minus b. What is the map? Yeah, a2 plus t minus b1. Sorry, a2 plus t minus b1. That going to gamma of the 2 of that. Okay, this map is of course c1. This is first degree polynomial. Therefore, it's actually c1, and this map is c1 because this, where does it land? This lands in a2 b2, right? Therefore, this is again c1. Therefore, this is also c1. Have you understood? So what I have shown now, therefore gamma is a path, that is piecewise c1 path. Okay, this is very important. Learn this. And one important thing is, do not try to memorize this formula. Okay, this interval I explained all of them geometrically. How do you get the new interval, and how do you define in the second part b1 to the rest of the interval, how to define that also we saw. It has to start with a2, and then as t varies from that, t minus b1. Yeah, right. So this is the concatenation. Okay, so now what we have done is we have done explain a path, what is meant by a continuous path, what is meant by a C1 path, what is meant by a piecewise C1 path. Hereafter path actually means piecewise smooth or piecewise C1 path. Okay, we gave a lot of examples, and one more important thing we learned is concatenation. That is two paths. If the end point of the first path is the initial point of the second path, then I can get a new path. Okay, that is again a path. We checked all those things. Okay, and if you look at my example 4, where I had a line from going from 0 1 to 1 plus I, and the other one which is minus 1 to minus 1 to plus 1, and then from there 1 to 2. These are all piecewise smooth path, and this is how we are done. Okay, these are also concatenation. You understand that? Isn't it beautiful? Yeah, if you want to arrive at the formula which I have done, again you can do that. Okay, try it. In the next lecture, we will talk about how to integrate a function along a path. Okay, so stay tuned. We will meet again.